Yes. And we are back live one more time. The chat, once again, doesn't want to load on a laptop. No worries. I can get the chat to load right here. There we go. See? I got the chat right there. Just so you know, little inception thing right there. But yeah, even if it doesn't load on the Chromebook, laptop, or whatever it is, I can still get it to load right where I'm standing. Let me go. Yes. Yeah. Okay. I'm gonna put something in the door. Hold on 1 second. I forgot to take care of this earlier. There we go. There we go. Excellent. Okay. And do that there. There we go. So, in regards to today, my entire goal for today is to focus entirely on the divine proportion / golden rectangle, golden spiral, like this one thing known as the ratio of phi. I have some visual things to kind of go over with you in regards to it. I have one video that is a little bit skeptical of the whole thing being with the quote unquote divine proportion, but I do like the examples that are brought up. But again, I'll bring that video up a little bit later. My intention for the beginning of this class period is to focus on exactly how phi is calculated, how it is defined, things of that nature. I did remember to bring in an apple with a knife. Hopefully I won't cut myself, but I will be able to show you something on the overhead under the Elmo camera with that divine proportion. It's absolutely phenomenal. But we'll see what happens there. So for those of you in the chat, if you haven't done so already, definitely leave a comment in that chat. I can see the comments that have been left so far. Thank you so much for that. And just to kind of get this thing started, if you would, if you do not already have them out, I'm going to need those notebooks out and open. Let's do this. So, I'm also going to open this. Apparently, I don't want to do air conditioning for some stinking reason. Patrick, when you do fantasy baseball, do you guys do categories or do you do like points? Okay. We do categories. We do 12 categories. So it is entirely possible to do a tie 6-6. I lost to Getty's 6-5-1. He won 6, I won 5, and we tied. What the heck? Just come on. I'm 4-1 now. I'm not bitter. I'm a little bitter. Regardless, we'll get this thing moving. How's your team?
It's all right. It's one player's getting hurt.
Is it Springer?
Springer, Rendell, and now DeGrom.
Yeah, I have Springer. I have him on my bench again. Goodness gracious. All right, back to this. So the first thing that I want to do is one of the more basic definitions as to what phi and the golden ratio actually is. So I'm going to call this divine proportion continued. Today is the 11th. Now, in order to actually calculate the value of phi, there actually is a nifty algebraic way of calculating the value of phi, and it's kind of nice, actually. It really, really is. Now, let me just show this to you. Now, what I'm going to show you is something that was not known by the ancient people in terms of the numerical value. They didn't know the numerical value of phi. They just knew that this ratio was divine in nature, or they felt that this ratio was divine in nature, that they were able to incorporate it into their architecture and into their art and into everything in between, just because they saw it everywhere. But basically, imagine that this line is a certain length, and I have 3 points that I am focusing on, these 3 points on that particular line. Now, for the sake of argument, one might argue that the length of the longer portion is A, and the length of the smaller portion is B. The way that phi is typically defined, it's defined in a number of different ways and a number of different phrases. But what they basically say is, okay, the length of the entire line to the length of the longer portion. Now, this is a ratio. This is a ratio. A ratio is just a fraction. Ratio, rational, all that fun stuff. But what they're basically saying is the length of the entire thing, which is A plus B, in a ratio with the larger part, is equal to the ratio of that longer part to the shorter part. There's a lot of different ways to define that, and I'm going to show you one of the classical ways of saying that statement. But this is the algebraic way of expressing that idea. This weird A-B relationship is going to produce the value of phi. And it's going to be kind of nice, actually. It really is going to be kind of nice. You'll see what I mean in a moment. I'm going to solve this thing, but before I solve this thing, let's just do one thing. We actually know it. Yeah. We're going to do this. We're going to let B equal 1, and we're going to let A equal phi. We're going to let B equal 1, and we're going to let A equal phi. And this is how we're actually going to end up solving. It's going to be a little weird, I know, but let me restate this little fractional relationship right here. So then all of a sudden, instead of A plus B over A, I have phi plus 1 over phi equals phi over 1. We're going to solve this. Phi is acting as a variable. It's acting as a variable that we are going to have to solve. And we are. And you'll see how it kind of shows up in a little bit. It's going to be weird. It's going to be very weird. But we're going to get this thing done. In fact, let me actually get the picture, the image of it in my book in a moment. I was actually able to remember to bring in this book. I've had this book for like so many stinking years. Somebody got this for me as a gift in college, and I thought it was fantastic. It's called Divine Proportion, Phi in Art, Nature, and Science. It's one of the first mathematical books that really clued me into what phi actually was. Weird question. Do you guys have any recollection of a world before YouTube? You can't remember a time where YouTube didn't exist? Okay. I got this book in a time where YouTube didn't exist. I couldn't just go on YouTube and be like, what the heck is phi? Like, look up a quick video on it. I actually had to read through the book in order to get this thing done, which is, kind of whatever, but it is what it is. But what I really wanted to do, I think it's over here. Yes. Should have marked this thing up. There it is. It's this relationship. I'm gonna pull this back in a moment, but this relationship is expressed through this weird thing in the book. And I'm not gonna have you copy down what's in the book, obviously, but I'm gonna read to you what's actually in the book. It says that Euclid, the famous Greek mathematician, who first put the divine proportion into words, divided a line into two sections in such a way that the ratio of the whole line to the larger portion is the same as the larger portion to the smaller portion. That's generally what I just expressed on paper. And I'm going to zoom back out and show you what I wrote on paper again. But this is how they generally expressed the idea of phi back in the day. They did not know the numerical value of phi. They didn't. The Egyptians didn't have a number system that we would recognize. The Sumerians and the Greeks did not have a number system that we would recognize. They didn't have it's a 1.618. They had no idea what decimals were. They didn't have that. In fact, okay, the Greeks, you guys know the general idea of Pythagoras and the Pythagorean theorem from geometry? Yeah, it's one of the things that most kids kind of remember from high school, the idea of a squared plus b squared equals c squared. But there is a way to actually draw a triangle, a right angle triangle with sides 1 and 1. And I'll kind of just, when I'll put this on a post-it, you don't have to write this one down. I just want to show you this because I just wanted to show you how messed up it is. Ancient civilizations and the way that numbers work out. You know the Pythagorean theorem, but if you had a right angle triangle with 1 and 1, 1 squared plus 1 squared would equal c squared, c being right there, where you would get 2 equals c squared, or c would equal the square root of 2. And you look at that today, and you're like, okay, yeah, I know the Pythagorean theorem. You know that a squared plus b squared equals c squared. I know the square root of 2 is a number. I know that the calculator can spit out that number. But the ancient Greeks had no idea what that was. The ancient Greeks had no way of expressing what the heck is a number that can't be expressed as a fraction, a number with that cannot be expressed in simple terms. What the heck is this? They didn't know what to do with it. Thankfully, even though they didn't know exactly what to do with phi, they were able to express it in this visual form, which is nice. And we're going to see these visual forms in architecture, in art, in some of the videos that I have for you later on. Well, let's solve this. We do have to solve this. I did not teach any of you algebra. Actually, no, I told people online I taught algebra. None of you in class I taught algebra. Actually, I think every single one of you online I taught you algebra 2, but I didn't teach you algebra 1. But regardless, I'm going off on a tangent. I'm going to do a little butterfly method. Some people call it the butterfly, but I'm going to cross multiply. I am going to cross multiply on these two fractions because I'm going to attempt to solve for phi. On the one side, I'm going to get phi times phi, which is phi squared. And on the other side, I'm going to get phi plus 1 because it would be multiplied by 1. I'm going to solve this. Not to take you back to your algebra 2 skills, but if you were to get one side of the equation equal to 0, just like that, we could solve this. This can be solved using the quadratic formula. Now, again, the Pythagoreans, the Egyptians, the Sumerians, they didn't know what this was. They had no concept of what a quadratic formula was or how to solve quadratics or anything like that. The only thing that they immediately recognized was this relationship of these lines. The relationship of the ratio of the whole to the larger is equal to the larger to the smaller. That's how they recognized it. But in modern terms, we can solve this. In terms of the quadratic formula, I'm not going to bore you with the details, but it goes negative b. And notice I'm not writing the letters, I'm putting in the numbers. Negative b plus or minus the square root of b squared minus 4 times a times c. The whole thing is over 2 times a. Notice how I wrote that thing in. I'll zoom in on that portion over here. To simplify that quadratic down, we would end up getting 1 plus or minus the square root of 5 over 2. This is the exact value of phi. This weird looking fraction. I mean, I'm going to show you in the calculator what that numerical value is, but this fraction of 1 plus or minus the square root of 5 over 2 is the exact value of phi. The ancients did not know what that was. They didn't have a numerical value in decimal notation. They didn't have a numerical value. They didn't know what these symbols meant. They had their own way of expressing the mathematics behind it. And I'm going to show you a couple of those expressions today. But let me show you on the calculator what this actually looks like. Zoom in, zoom in, zoom in, zoom in. Come on, there we go. Parentheses, 1 plus the square root of 5, close those parentheses, double time for the top of the fraction, divided by 2. There it is. That is the exact value of phi. You wouldn't do the minus. The minus would just give you that's meaningless at the point right now. That's not actually what we wanted. We wanted that one. This is the exact value. This is the number that is, well, in some people's opinions, divinely inspired. It seems arbitrary that a number like this would govern the universe. It seems arbitrary. Why this decimal? Well, like I said, I do have videos kind of showing you that in a little bit. But it is this decimal that runs everything. Almost everything. It's insane. This is approximately 1.61803 ... keeps going forever. Absolutely insane. So, where's that thing? Where'd I put them? There they are. Now, for those of you that are online, I do have a PDF to show you, but I'm going to hand this actual physical paper to the people that are here. So, this is what I ran to the printer for. Because this thing, this is going to be interesting. This is going to be interesting. Again, the ancients had no way of really expressing what this was in our modern terms. So we're going to go back to the way that they expressed it. For those of you online, I just posted a PDF that looks like this. Now, it does look kind of weird. I'm going to point out a couple things for you on the live stream. For you guys that are here, I mean, clearly you can see the darkened lines on the grid, right? Yeah. But for those of you on the computers, it is a little bit difficult to see this. So I'm going to hold something up to the camera real quick, just to kind of show you. So this PDF should really look like this. This PDF should really look like this. And I'm going to try and point that out on the screen in a moment. But hopefully you can kind of see, and I'm going to try and point to this right here. There's 2 1x1 boxes, and then there's a 2x2 box, and then there's a 3x3 box. I'm going to actually show you how to draw this out on paper. And then this larger one, we're going to do something else with in a little bit. So it is a little bit difficult to see on this one. I do apologize for that. But there's got a box there and a box there, and then that box there, and that box there, and that box there. And it keeps going. It keeps going in this neat little spiral way. And I'm going to show you how to actually construct that on your own. So again, I thought that was going to show up better. Maybe I could send you the, yeah, I could do that. Hold on, let me see if I can send you something better. I have an idea. Oop. Yeah, as to how to do this. But let me show you how to construct this first. Let me show you how to construct this first. So what I'm trying to show you is a bunch of little squares that do this. You start off with a 1x1 square. You start off with a 1x1 square. Then, right next to it, I'm going to go right on top of it, I'm going to do another 1x1 square. So I started off with a 1x1 square and then a 1x1 square. Cool. Then directly to the left of it, I am going to do a 2 by 2 square. I'm going to do a 2 by 2 square, and it kind of fills that thing in. Then directly below it, I am going to do a 3 by 3 square. Now, the reason why I'm doing a 3 by 3 square, I mean, hopefully you can see that the length of the bottom of these 1s and 2s, it goes like 1 and then 2, 3. So there's a 3 by 3 square right there. And then right here, you can see the length. It's a 1, 2, and then 1, 2, 3. That's 5 altogether. So I can go 1, 2, 3, 4, 5. It's a little bit difficult on blank paper, which is why I have the grid. But then you have a 5 by 5 square. And what I'm actually trying to show you is that these squares, as they're being drawn according to the rules that I have inspired for you, it's actually creating a visual representation of the Fibonacci sequence. It's a visual representation of the Fibonacci sequence. I'm starting with a 1 and a 1, and then 1 plus 1 equals 2. And then 1 plus 2 gives you the 3. And then 2 plus 3 gives you the 5. And then 3 plus 5, well, the next one should give you the 8. And you can see that a little bit better right here. And like I said, I'm going to figure this out for you guys online in a moment. Let me actually freeze my screen here and then see if I can't figure this out. I have this. I think I can open that. Oh, I think I know what to do. Okay, hold on. Let me open up my Google Drive. Let me create a Google Sheet. Let me see if I can't copy and paste. It says working. Come on. I got a little circle ball thingy. That may or may not be doable. Let me see what I got here. Can I do that? Yeah, that kind of works. That kind of works a little bit better. Let me show you what I got here. Boom. I hope that does work. You can kind of see the grids a little bit. It's not that fantastic. Put that there. Let's see. What did I call this? I called this the golden rectangle. Let me see if this can actually work. Let me attach from the Google Drive recent golden rectangle. This is going to be terrible looking. I think that'll work, kind of. Let's hope. I'll give it a shot. Maybe they can actually see it. Maybe this will work better. Question mark. We'll see. I'll let them take a look at that when they get the chance. But let's go back to here. So what I'm going to do on this little golden spiral right here, and you guys can, obviously, when you're in the class with me, you can totally do this. But for those of you that are home, it gets a little bit dicey. But you can see that thing that I drew where it goes 1, 1, 2, 3, 5, 8, and it's doing this weird kind of little spiral thing. So what I'm going to suggest is that you start in this corner right here, in this corner where I'm pointing. Start in this little corner, and what I'm going to do is I'm going to draw a curved arc. And this curved arc is going to go from that one corner up to the top right corner. I tried to make it as curved as possible, but it's going to do this little curvy thing right here. It's going to be a bit more prominent in the larger rectangles. But then I reach the corner of the next square. And then what I'm going to do is I'm going to do the same thing. I'm just going to curve back like that. So it kind of does one of those. It's just basically mirroring the image because it's a 1 by 1 and a 1 by 1. And then I'm going to do the same thing in the 2 by 2, except with the 2 by 2, I'm going to go through this top right portion and this bottom left portion right here. And again, it's not going to be a straight line. It'll be a nice little curve like that. And basically, this curve, which looks somewhat circular, but the angle of the circularness is actually growing a little bit. It's a little weird. You're going to do the same thing through the 3x3. But the circularness of it all is expanding. And it's expanding at a ratio of phi, because the squares that we're making up here are made up of Fibonacci numbers. We started with a 1x1 and a 1x1. Then it went through a 2x2. Now we just went through a 3x3. And now we're about to go through a 5x5. Let's see if I can do this right here. I'm just going to prepare where this thing is going to go. Again, this thing is going to curve like that. It's not uniquely perfect here. I'm just trying to draw it the best that I can using modern, just kind of curving techniques with my brain. And obviously, the larger it goes, the more weird it is going to look. And I got to go through this 8x8 right here. I'm just prepping where this thing is going to curve through. There we go. I'll curve it through there as best I can. Obviously, if we had the proper tools for doing this, that would be a different thing. But what I'm just basically giving you is a rudimentary understanding as to what this spiral actually looks like. This is known as the golden rectangle, otherwise known as the golden spiral. I've also heard it referred to as the Archimedes spiral, but that's neither here nor there. I'm just going to kind of freehand that one. Didn't even really think about where that one was going. I probably should have curved that a tiny bit more. That's okay. Let's kind of eyeball it there. But this curve is supposed to be just one continuous smooth curve that looks like it is expanding every time. Oops, froze like my heart. That looks like it is expanding every time you get to a larger rectangle, and that is absolutely the case. Let's see this here. Good. Okay. Let me see if I can do this here. Yeah, I just literally went for that one. Now, the spirals on this thing get larger and larger and larger and larger the farther you go out on this. Obviously, computers can do a much better job nowadays. Yeah, I just went for it on that one. I totally messed up halfway through. I'll kind of just do this. There we go. But like I said, this spiral is going out in a weird kind of phi proportional loop-de-loop thing. It's weird. It's strange. But again, it is based solely on the Fibonacci sequence. Because you can see here, and I'll kind of write these in. Here we go. I'll write these in. But this one is a 1x1, a 1x1, a 2x2, a 3x3, a 5x5, an 8x8. This is 13x13. This is 21x21. And this is a 34x34. It's obviously a lot easier for me to do those using an Excel spreadsheet and a grid. I mean, they didn't have graph paper back in the day, but even though they didn't have a graph paper like this back in the day, they were still able to create stuff like this, which is absolutely phenomenal. Yeah, actually, fun fact, they didn't have the XY plane until a mathematician by the name of René Descartes. That's why they call it the Cartesian plane. It's kind of weird. But I did want to show you some things in this book. I wanted to get to the portion that has the spiral in it, just because it does look kind of awesome. And I'm going to get back to the apple there. And they do show some of these things in the video that I have for you. Better examples, but I do have, oh, come on, where are you, mollusk shell? It's not a mollusk shell. Science, nature, there we go, found it. Okay, that's the one I need. So just to show you right here in the book, the one on the left is actually known as the spiral of Archimedes. That's not the spiral that you just created. The spiral that you technically just created was something a bit more akin to this. This is known as the equiangular spiral. And it's something that actually does, like I said, show up in real life. In fact, kind of move this over a little bit and zoom in. Hopefully you can see this a little bit better. But these are two examples of real life shells, things that just show up in nature that do have those spirals that we were talking about. In fact, actually, this is probably a better example of it. This is a chambered nautilus shell. This is a chambered nautilus shell. And this chambered nautilus shell does the exact same spiral that you just drew. This is just a cross-section of that spiral, or of that shell, I should say, which is absolutely insane to me, to think that something that you can draw on paper using basic Fibonacci numbers is something that actually shows up in a real-life situation right there. It has the exact same proportions. I mean, obviously, if they drew it correctly. And then you can see here's an example of what they drew using that golden rectangle. It's kind of nice. And then obviously you're going to see this in a little bit, but then here's an example of a what they call a free-floating ocean snail with the same kind of spiral in it. But that spiral is also recognized in a spiral of a hurricane. It has the same exact type of a spiral where it expands at a ratio of phi. It's absolutely insane. This is the weirdest thing right there. Hold on. I'll cover up what that thing is. Hold on. There we go. Does anyone know what the heck that is? It's a bone inside your ear. It's a bone. I covered up it at the bottom right here. Look at that. It's the cochlea of the human inner ear, the organ responsible for hearing. It's legit inside your body right there. And it expands at the ratio of phi. Look at this one right here. This one's really messed up. The coloring's a little off. But this is actually an empty hair follicle. An empty hair follicle. Again, showing that spiral, any type of, not any type of spiral, but most spirals that are naturally created in the world expand at a ratio of phi. It is absolutely insane the way that this thing goes. Yeah, I don't want to do that one just yet. Yeah, actually, the video shows this one a little bit better. But we're talking about the leaves the other day, the leaves that grow out to get like the sunlight. The way that they kind of do, you can see this thing kind of spiraling around. It does more of an Archimedes spiral, but the ratio at which those things come out are in the ratio of phi. It's insane. Now, not only this, like, what does this shape kind of remind you of? What does this spirally shape remind you of? Something besides plants and science. Or within the realm of science, I should say. I don't know when you actually learn this. What class do you guys learn about DNA? Biology. It's basically a DNA spiral. It's insane. The way that everything just kind of relates to each other. I don't know. Anyway, then it gets into more of the sciencey type stuff, which I'm going to get into with you guys in a little bit. It's going to be nice. I really like that book. It's fantastic. Okay. So, okay. Good. Now, I wanted to show you this because I wanted to try and draw this, but in reality, it's difficult for me to draw this. So let me do this, and I'm going to show you something here. I'm not going to have you draw this. I'm going to have you just kind of look at what I want to show you right here. Boom. And actually, that's a perfect one. Open up in a new image, and that one as well. Open up in a new image. Boom. Okay. So like I said, I'm not going to have you draw this, but this is a basic five-pointed star. The five-pointed star that most people are able to create in elementary school when they just want to draw stars or whatever. And that's the first one that you learn how to do. It's like, oh, hold on, yeah. That's like, I remember how to do it. It's like, da, 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 da. Yes, five-pointed star. Exactly. Cool, fantastic. But this five-pointed star, if drawn correctly, if drawn like a regular pentagon, let's say, pentagonal shape, hides all of these ratios of phi. And I want to point out right here, look at this insane thing right here. This green to red length right here is in the ratio of phi, the very first one that we drew today. And you can actually, with this thing, you can create or fit that spiral directly on top of what we just drew earlier. It is absolutely insane how this thing just kind of flows out. Now, I'm showing you this image for a reason, because I have an apple that I'm about to cut open. But I want to show you one more image before I actually do that. The other image being right here. Boom, there we go. That image, oh, I could probably zoom in a little bit on that one. Will it let me? Yeah, it will let me. Cool. But again, you see this pentagonal shape and this 5-pointed star on the inside. And they have all of these different lines marked out. They're basically saying like, okay, if the length of this part of the star right here is 1, if that is 1, then the relationship between this orange line and this green line, well, that would have a length of phi. And this would have a length of phi squared, and this would have a length of 5 cubed. Everything just kind of relates back to that idea of phi in a natural way. And it shows off this natural sense of beauty. It is insane to think that just, again, I talked about this last time, but that this number, this ratio, this concept is just embedded in everything that we have thought and done has been beautiful over the years. So, here we go. I'm going to zoom out here. I have a little experiment. I brought an apple and I brought a knife. Please don't tell anyone that I brought a knife to school. There it is. I don't care. I really don't. But I have this apple. I've seen people do tons of things with apples. You ever see somebody try to rip it open with their bare hands? Have they, in real life? I thought about it. I'm like, I could do that. I'm like, no, I'm not going to do that. So we just have a regular old apple right here, right? Nothing special about it. I ripped out the stem because I don't like the stem on there. But I'm going to try as best I can without hurting myself. I am going to try and cut this thing horizontally. Now, I do have a backup apple just in case. Just so you know, I do have a backup apple. But look at that crap right there. I just cut this apple open horizontally. And I'm going to zoom in on this thing right here. Look at this. Within the confines of that apple. Now, again, it's not absolutely perfect because I didn't cut it precisely the way it should go. But you can see the orientation of of the chambers on the inside of an apple. On the inside of an apple, like people don't eat the core, right? And how do people usually eat an apple? They eat it around the core in such a way where you just have like the top and the bottom of the apple when you're done. You never see the inside of that core. But you do know on the inside of that core, the reason why you don't eat it is because it's a bit, oh, hold on. The universe is shaped like a human? Is what she said. I'll talk. Okay. Tiana did ask a question about DNA. I'm going to talk about that in a moment. I'm going to come back to that. I will double back to that, but let me finish up my apple example. You guys don't typically look within the chambers of this apple, but you know there are seeds in there. But those seeds grow within these chambers that are shaped like a pentagon. And this pentagon is drawn with the ratio of phi in mind. It's just a simple apple. Yet it contains the exact proportions that we have been going over time and time and time again. Now, I'm going to actually eat this a little bit later, but I want to double back to Tiana's question about DNA. DNA phi. It's called sacred geometry. It's kind of like the study of it. It's called sacred geometry. I wasn't intending on going down this path, but it's a very good question. I just wanted to kind of go through it. So you guys generally know what the shape of DNA looks like. It's a spiral. It's a spiral that kind of goes up. And this image is not really that helpful. Let me go back. Yeah, get out of there. Let me go to the images. Maybe the images will help me out a little bit better. Heck yeah. There we go. That's probably a little bit better. So this is the generally accepted shape of DNA. Open up this image in a new tab. This is the generally accepted shape of DNA. Now, obviously, DNA comes in a spiral. But the way that this spiral, not expands, I should say, but as the spiral kind of goes around, each of these spirals are within a proportion of phi to each other, depending on where you kind of measure it from. And you can even see right at the top of the screen where they have something called a minor groove and a major groove. And that looks strikingly similar to the very first thing that we drew today, this line where I labeled it A and B, where I was able to get the exact numerical value of phi. Major and minor groove. Absolutely insane. But then, check this out. Phi, galaxy. Let's just see what happens there. I don't know if it'll actually work the way I want it to. Yeah, oh, there it is. Boom. There's a good one right there. There is a spiral galaxy. I don't know what spiral galaxy this is, but that spiral galaxy is expanding exactly like the spiral that we literally just drew earlier that expands at the ratio of phi, that we can draw using square boxes within the measurements of the Fibonacci sequence. I really hope that shows up on the online a little bit. Yeah, it is a little bit difficult to see. Yeah, I apologize for that. Now, I have a video to show you. Now. I am going to put this link. I'm going to put this link on the Google Classroom stream. So in case that you can't see it that well, and while this video is playing, I am going to enjoy my apple. I can't give you guys apple. But let me go back to my channel playlist. There we go. And let me open up this thing. And I'm going to have to alter the volume, make it a little bit louder for people to see. Actually, yeah, I forgot to put the link. So let's see. Share, embed. No, I don't want to embed. Share, copy. And I will throw this into the Google Classroom stream just in case you wanted to watch it there. There we go. But I am going to have this thing playing. Here we go. Turn up the volume. Let's see how this goes.
Has always been in search of patterns.
Yep, there we go.
Humanity has always been in search of patterns. They make us feel comfortable. They give us meaning. Whether they be in the deepest, most conceptually difficult topics like string theory and quantum mechanics, or even in simple things like the behavior of the person we're talking to. We love to seek patterns, and do so sometimes against our better judgment. Nature and mathematics are no exception to that list when it comes to pattern seeking. In fact, it's at the forefront of it. We've evolved to notice patterns and be alerted when something isn't right. One of these so-called patterns that has fascinated mathematicians and individuals alike for centuries is the golden ratio. Also known by the Greek letter phi, it can be defined by taking a line and breaking it into two separate pieces. If the ratio between these two new portions is the same as the ratio between the original line and the now larger piece, the portions are said to satisfy the golden ratio. The value that satisfies this equation is roughly 1.618. It's an irrational number, meaning we can't represent it using the ratio of two whole numbers. In fact, we can't even write the number fully. It's unending. It's effectively the same as pi in that regard, and so we use the dots to represent the non-terminating nature of this number. But what makes this ratio so golden? The golden part of the name is rather modern. The more original name that was given to this ratio was the divine proportion. And right away, you can see that the term implies some sort of divinity, an extraordinary property that people must have noticed when they were dealing with this number. To further explain this fascination, we should begin by dividing the fascination into two parts: mathematics and aesthetics. The golden ratio and the Fibonacci sequence appear in nature every day, and arguably the strongest evidence of goldenness in the golden ratio is in the floral arrangement of seeds. Take this for example. If you were a sunflower, how much of a turn would you make before you made a new seed? It's a weird question, but it's an important one. If you don't make a turn at all, will you just continue making a straight line of seeds? That's kind of boring. If you make half a turn, or a 180-degree turn each time, well, now you have a line of seeds, but in opposite directions. 120 degrees gives you 3 lines, 144 degrees gives you 5 lines. There should exist some angle, some number of turns that, if properly executed, produces a pattern of seeds that is closely packed together with no gaps between them. Something like this. This seems more natural to nature, right? The number of turns needed to produce a spiral design like this is, well, the golden ratio. 1 seed placed every 1.618 turns, or every 137.5 degrees. This is known as the golden angle, and it is seen throughout all of nature. The idea is to arrange seeds in a way that can maximize the sunlight and rain that they receive, so that the genetic material can successfully be passed on to the next generation. If you don't do this efficiently, evolution won't be very kind to you. If you pack in the seeds too tightly, all the seeds won't get the nutrients they need. If you pack them too sparsely, you're just wasting space. This happens with not only sunflower seeds, but in plant leaves, tree branches, and even more. In fact, it goes even deeper. If you were to count the number of spiral arms in both directions, left and right, you'll find that they aren't equal. However, they will both always be Fibonacci numbers. The higher and higher the numbers go, the closer and closer the ratio between them approaches phi. The beautiful spirals that result are purely a creation of nature. These spirals are consistent across different flower types, and even the number of petals seem to be related to the golden ratio. The sunflower example is particularly interesting because it actually ties the aesthetic element of the golden ratio to the mathematics behind it. There's a reason why the golden ratio is used in flowers, and any other value doesn't seem to work very well. But what does that really tell us about the underlying and possibly grand design of the universe? We're all somewhat familiar with the aesthetic elements of the divine proportion. The idea is that visually pleasing faces tend to have proportions that are somewhat close to the golden ratio. The closer you are to it, the more beautiful your face should be. This inclination of harmony extends to the rest of the body as well, with many claiming that Da Vinci's Vitruvian Man demonstrates that the human body owes its beauty to the golden ratio. The phenomenon also has its place in architecture, with claims thrown around that structures as old as the pyramids of Egypt are in some way, shape, or form inspired by the golden ratio. Except for the fact that there's hardly any evidence that the Egyptians even knew this ratio existed. All of these beliefs contributed to the idea of the golden ratio and made it what it is today. The mathematical beauty is undeniable. It's proven. However, it's generally hard to verify any of these claims regarding its aesthetic purpose in our lives. For one, it's not sufficient for a structure to just have the golden ratio somewhere. It must be meaningfully incorporated and be the result of someone's conscious or subconscious choice. But what does meaningful incorporation entail? Why would you choose the ratio of, say, this pillar with that one and not with another? And then there's questions of measurement. Oftentimes, you see pictures thrown around the internet with a famous celebrity's face with random lines drawn on them that claim to satisfy the divine proportion. Long story short, they're reaching pretty hard. Without proper definitions of the facial features they're referring to, like what a cheekbone is, where it starts and ends, and so on, there's basically no scientifically verifiable structure to what they're claiming. Even if you do find that a certain arrangement and placement of measurements do wind up representing the golden ratio very well, it's never quite exactly that. Despite these claims, however, one could still argue about the idea of facial beauty and the importance of the golden ratio in it. All that matters is our perception of something. If the ratio of some facial feature is close enough to the golden ratio, so much so that we're unable to distinguish it from the actual ratio itself, and we find it pleasing, wouldn't you say that the aesthetic element of the golden ratio is justified? To investigate this point, experiments have been conducted relatively recently using a geometric object that has the golden ratio written all over it. It's the golden rectangle. It's any rectangle that has sides A, B that satisfies the relationship I just described at the start of the video. Except this time, it's a shape and not just lines. The experiments include showing participants many different rectangles of different proportions, with one or more of them being golden rectangles. They were then asked to choose which rectangle they felt represented the ratio best. If the hypothesis that things with the golden ratio embedded in them are more attractive to us is indeed true, you would expect to see a significant number of participants choosing the golden rectangles. But, turns out, the evidence is not so great on this one. Instead of choosing the golden rectangle, participants seem to prefer rectangles around that number, like 1.5 or 1.75. It's close, but it already somewhat disproves the idea of the golden ratio. If a rough value around the golden ratio is good enough, then the ratio itself isn't so golden after all. But even if, say, the preferences do seem to be around that golden ratio, there are theories as to why that might be. People who are more aware of the golden ratio might be predisposed to having a preference toward it because of its place in history and mathematics. Besides, if you spend a lot of time staring at a screen with aspect ratios relatively close to that of the golden ratio, something like a 16:9 monitor, you will unintentionally find them more attractive. But now it would be a fair question to ask, well, what started this golden trend? There does seem to be a sincere focus on the golden ratio in modern design language, especially with UI/UX design. While no designer in their right mind would swear by one single rule, the golden ratio has seemingly become a mainstay in graphic design. For example, a lot of websites tend to have headings that are 1.6 times the font size of the general text. Website layouts also incorporate golden rectangles. Again, once something like the golden ratio has been generally accepted as something divine, it's very hard to distinguish whether its desirability stems simply from its familiarity in our lives or from some deeper meaning. But it just so turns out that there is some deeper meaning, deeper inside us. There's a body of research that focuses instead on deeper biology and how the golden ratio plays a crucial role in it. The cardiovascular system is of keen interest in this regard. This is because it's one of those biological systems that has very small differences across ethnic groups. So, if the golden ratio were to be found in such a system, we could claim that it is indeed a more universal phenomenon, rather than existing simply due to some ethnic variation or bias. The cardiovascular system is deep within us. It runs our lives. There is no element of fabrication down there. Evidence found here would much better support the idea that there is some natural significance to the golden ratio. And in fact, there is. Your heart has many moving parts that help keep your body functioning. One of them being the left ventricle. It's what helps pump oxygen throughout your body. Now, the average ratio of left ventricle horizontal and vertical lengths of over 1,400 Swedish and Chinese subjects was found to be 1.618, awfully close to the golden ratio. Patients with left ventricle ratios that were further away from this value were deemed to have poorer functioning hearts. And as we age, our hearts tend to lose some of their power. Your blood begins to pump slower and slower throughout your body. Even the age-related cardiovascular decline was related to the golden ratio, with an early diastolic velocity decline of 1.6 centimeters per second per decade. On the other side of the spectrum, the early diastolic flow velocity of muscles in the heart of a growing fetus increases by 1.6 millimeters per second per week. It's remarkable how these and other metrics of cardiovascular health hover close to this special value. But even in these examples, there's still a bias in choice of units. For example, why is this particular metric in millimeters per second and not inches per second? Such choices could alter these quantities and take away the divinity in them. But why? If there isn't so much evidence behind the divinity of the golden ratio, why do people have this obsession over it? It's the same reason why we once believed the Earth was the center of the universe. We want to believe these things. Of course, people have moved on from those particular beliefs to more modern and sophisticated ones, like how the Earth is flat and all. But the core philosophy remains the same. We love patterns, and we love them even more if they make us seem special. Why did the golden ratio only have to do with our faces and not those of other animals? What about the body proportions of a snake? It's only human to only care about ourselves. This also highlights the age-old question about whether math is invented or discovered. You see, the phenomenon of the golden ratio existed long before we had any idea of it. The flowers arranged themselves without us having a cognition of numbers or mathematics. Even when we tried forcing our hand on certain elements of the golden ratio to suit our narratives of existence, the golden ratio itself didn't change. If the golden ratio were from a different time and were named differently, we would still be talking about the same thing, only with a different name. It was what it was, and it always will be, whether we have any cognition of it or not. There are things, properties of math and science out there that exist currently, right in front of us perhaps, and we have zero idea of what they are or what they entail. We may define things along the way, just as we have given the ratio a name, but the underlying mathematical properties remain unchanged. In truth, the divine proportion owes its divinity not to some all-pervading transcendental property, but rather to the idea of beauty and perfection that we've imposed on it. This beauty we seek is quite possibly not concentrated in one golden number, and even if it is, the golden ratio is probably not the one. In trying to find perfection, we can nonetheless keep defining phi. But remember, it's irrational. Phi does not end, and neither does our search for beauty in the universe we live in.
So this guy is trying to be a little bit more poetic, but I did like the way that he described certain things. The one thing that I will debate him on is the fact that he said, like, okay, why are they measuring the ratio of phi in millimeters per second? Well, it doesn't matter if you're doing millimeters per second or if you're doing like inches per second. The ratio is going to remain the same. It doesn't matter what type of unit you end up using. So that's one thing there. He also talked about mathematics being discovered versus being created. I am a firm believer that mathematics is discovered, but the words and notation that we use are created. So we call it phi, and we define it to be 1.618. However, if this were another like alternate universe where they used a different type of notation and language, perhaps we would be in a completely different number system. Doesn't matter. But in that other number system, this ratio, this image of a ratio would still exist. I do have one more video to show, but before we do, I do want to draw one more thing into our notes. I wanted to talk about the Great Pyramids of Giza. Now, there's a lot of information about the mathematics behind the Great Pyramids of Giza, and how they oriented them, and how the three pyramids are in the shape of Orion's belt, the constellation up in the sky. There's a whole bunch of information in regards to just the mathematical accuracy and how like it's a massive, massive project, yet they were able to build this thing with just such stinking accuracy. It is absolutely insane. So I wanted to draw an image for you that I wanted you to copy as well. So you have a pyramid. Now, if you want to just draw a pyramid, you can just draw a square at first, and then a point somewhere up top, and then each vertex or corner of that original square connects down to that base. That's the way that a pyramid is generally drawn. That's a weird way of drawing it. Let me try it again with a sideways thing right here. See if this works a little bit better. Put it up there. See if I can connect them, make it look a little bit better. But you kind of have to. That one wasn't as good. Yeah, that one wasn't as good. But you have a pyramid basically. Pyramid. Boom. So now we have the pyramids of Egypt. Now the Great Pyramid of Egypt, the very Great Pyramid, has a height. And let's see, there is kind of the base right there. And there is the slope. So this is the slopey part of it all. This is the base. It's not us. And the thing that I wanted to point out, oh, you can't see it. The thing that I wanted to point out about the Egyptian pyramid and its height versus its slope versus its base is the fact that this triangle that you can draw from the very tip of the Pyramid of Giza, I don't know how tall it is, but let's just say that the base was 1. Well, the length of the slope has a ratio of phi. If you were to take the length of the slope of the pyramid and divide it by, well, technically half the base, because I'm going from the middle of that height all the way to the edge right here, the pyramids of Giza reflect that ratio to perfection. But not only that, the height of the pyramids are in the exact ratio of the square root of phi. Let me zoom in on that. The pyramids of Giza have this relationship between the height of the pyramid, the slope of the side, and half the base. They have that exact relationship. It is absolutely insane to me to think that something like that happens. Insane. I did want to show you one thing on the calculator real quick because I thought that this was awesome in regards to phi and its relationship and whatnot. But it's just insane. I'm going to leave that there for a moment and bring this in. Check this out. So we calculated, you don't have to write this down. I just want you to see this. This just blows my mind. We calculated the 1 plus the square root of 5 divided by 2 like that. There's phi. I'm going to store that to a variable. I'm going to store that to the variable x, just so it's there. You can see that there's x. Now, check this out. This is just absolutely insane to me. X plus 1 is this number. That's just phi plus 1. X squared, which is going to take 1.618033989 and multiply it by itself. Has that exact same decimal structure still. It doesn't matter if you take the original phi with that decimal structure of 0.618033989 or square it, meaning you multiply it by itself, you end up with the exact same decimal structure. That just completely messes my head. I don't even know. Okay. I do have one more video to show you, and then that's going to wrap up today. I do have one more video to kind of show in my playlist right here. I believe that this one was better.
They say
yes.
It's impossible to make more while using
So
less.
just got to get past the commercial.
Uniting industrial
This one I think will be a little bit easier to see.
to shape a sustainable future.
Come on, advertisement.
Aviva will take you there.
Okay.
Divine number or design myth. How much do you know about the golden ratio? Since the time of the ancient Greeks, artists, designers, thinkers, scientists, and engineers have been fascinated by the golden ratio. Also denoted as phi, the golden ratio has, over the centuries, even been considered as the perfect illustration of beauty. For the uninitiated, the golden ratio, also called the golden mean, the golden section, or the divine proportion, is one of the most famous irrational numbers. Like another famous irrational number, pi, the golden ratio goes on forever. This mathematical concept is said to appear in nature and in various iconic pieces of...
So I'm going to pause it right there. Look at those iconic pieces. And yes, we've seen the Vitruvian Man in the middle. But look at the one on the far left. You have that Archimedes spiral occurring precisely... Actually, I shouldn't say Archimedes spiral. But that golden spiral occurring precisely in the dimensions of the Mona Lisa. You have the line that I drew, the very first thing I drew today, showing the dimensions of the shape of the Eiffel Tower, just making it appealing to the eye. Back to the video.
Of art. It has allegedly inspired artists like Michelangelo and Leonardo da Vinci. The Mayans, ancient Greeks, and Egyptians are all said to have incorporated this divine number into works of art and architecture, such as the Parthenon in Greece, although it is not really known if these were intentionally designed that way. Some researchers also feel that the importance of phi in nature and culture has been vastly overblown. So what is the golden ratio? The golden ratio was first described in Euclid's Elements around 2300 years ago. It is found by dividing a line in two parts so that the long part divided by the short part is equal to the whole length divided by the long part. The number that results is also related to the Fibonacci sequence. As a quick refresher, each number in the Fibonacci sequence after the first ones is derived by adding the two numbers before it. The ratio of each number to the previous number in the Fibonacci sequence is equal to phi, which is usually approximated as 1.618. Things get really fun though when you demonstrate this geometrically. That is because if you were to draw squares with the dimensions of the numbers in the sequence, you would create the famous golden rectangle. The harmony and proportions of the golden ratio were recognized by mathematicians like Aristotle, Pythagoras, Muhammad ibn Musa al-Khwarizmi, and Boethius, with some believing that the golden ratio could be the key to unlocking the divine secrets of the universe. The golden ratio has also been seen as a standard for beauty and aesthetics. Why? One reason is because it seems to appear often in nature. However, this is not as common as many think. The idea that the golden ratio is universally found everywhere is an exaggeration. The shape of the pine cone, Romanesco broccoli, and the shell of the nautilus are often given as typical examples of the golden ratio. However, none of these really follows the proportions of the golden ratio.
Yes, they do. I don't know what this guy is actually saying. It depends on how you actually draw this thing.
You can also find the Fibonacci sequence in nature. The petals and leaves of plants are sometimes found within this pattern. However, not every plant behaves this way, so you cannot call this a universal property. This does not make the golden ratio any less interesting or valuable. Do we use the golden ratio today? Yes and no. Artists and designers may sometimes use the golden ratio in creating everything from products to brand logos. There's been a lot of discussion as to whether or not Apple's logo uses the golden ratio, and it does not stop there. Though the consensus is that the frequency of appearance of the golden ratio is exaggerated, it may have practical uses. The Fibonacci sequence has been used in the world of engineering, in computer data structures and sorting algorithms, audio compression, and architectural engineering. The golden ratio has also been useful to researchers in fields like high-energy physics, quantum mechanics, and cryptography. For artists, there may be another factor. Because the golden ratio is pleasing to the eye, artists may also have an unconscious bias towards including it in their work. What do you think? Do you believe the importance of the golden ratio is a myth? Or is it nature's number? Leave your comments below.
See, I really like this guy because he's very much kind of trying to be a skeptic, I guess. See, the thing is, in the real world, things don't always hit the ratios of the divine proportion perfectly. For example, I mentioned this the other day, but I'll tell you the long form version of it. A few years ago, I taught this class, and I was teaching about the phi and the divine proportion and all this other stuff, and I showed them all these different examples and how it showed up and things of that nature and blah, blah, blah. I had like 20 kids in the class, and I had every single kid measure the length of their arm from the shoulder to the fingertip. I've mentioned this before, and from the elbow to the fingertip, and they all gave me their numbers. I put them into a calculator. I figured out the ratio for each and every single one of them. And the ratios were all different. Some of them had a ratio of 1.7. Some of them had a ratio of 1.4. Some of them had a ratio of 1.6. But when I took all 20 of them and averaged their ratios together, the average of the 20 people in my classroom, the ratio was 1.618. Now, I wasn't expecting it to be so perfect, but that's the general idea. It's not that every single plant in the world is going to have the exact proportion of phi or mixed into it, just like not every human being is going to match that ratio perfectly. But it's the average of all human beings. For example, like if I were to ask, like, what is the normal temperature for the human body? What would you say? 98.6. That's a myth. You know that's a myth? In reality, what ended up happening was this doctor wanted to find out what the average temperature was. He took the temperature of 100 people living in the town that he lived in, and he found 98.6. But, I mean, as you know from statistics, you took a sample of the 100 people in the town that you lived in. Cool. But 98.6 became the prevailing notion for years and years and years. In reality, 98.2. 98.2 is a bit closer to what it actually is, the average of all human beings. That's actually a really interesting experiment. I might want to try that one day because we got like those, like, not non-touch thermometers. I might try that. That would be interesting. Anyway, regardless of that, the time is 8:31. As I said, that was the last thing that I wanted to do today. We're going to wrap this up today. I have you guys again on Thursday, in which we are probably going to wrap up a bit of the divine proportions stuff that we've been talking about. And we'll kind of see where it goes from there. In the meantime, for those of you that are here and for those of you that are online, just in case, there are a few things recently that if you did not turn in, please make sure that you are working on that stuff. I have not checked I haven't checked the details of what people have turned in for the 4-color theorem project, but I believe I've caught up with other things. Like I've caught up with the most recent major that you guys did and the Hamilton projects. I went through those as well. So if there's something that you owe me, get them done, because progress reports are supposedly coming out, I believe, by the end of the week. Let me double check this. Progress reports, blah, 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 blah. They will close on the 17th, it says. Oh, that's Monday. Yeah, so progress reports will be sent out on Monday or close on Monday. I don't know. I don't know how those things work. Anyway, you guys have roughly 9 minutes or so, maybe 10 minutes or so. I'm going to leave the rest of the time to you. If in the chat, if you have not left a comment, please make sure that you do so. If you haven't already, I'll give you another few moments to do that. And otherwise, I'm going to be signing off in like 30 seconds or so. Woo. So the rest of the time for you guys is yours. Let's see here. Put up.